Hello everybody. This is my presentation for my Field Techniques final project, and so I wanted to make this video and talk about what I did for my project. So my project is residential land use suitability study for the Kansas City Northland region, particularly three sub areas within the Northland. I'll talk about that more on this slide. So the Kansas City Northland region is anything that is north of the Missouri River on the Missouri side, typically in Clay or Platte County, Missouri. So I'm looking at three areas within that: the Kansas City International Airport area, the Gashland area, and the Shoal Creek Valley area. So historically, this part of Kansas City suffered from poor planning, which led to urban sprawl, inefficient land use, high traffic volumes, as well as racial and wealth segregation, which is a big issue across Kansas City in general, but particularly this area. So in 2023, the city of Kansas City passed the Kansas City Spirit Playbook, which is a new comprehensive plan that favors contiguous development, looks to prevent sprawl, as well as has several components to address social equity issues. So for the land use suitability, I'm going to use the method identified in this book, Smart Land Use Analysis. It's the Lucas model, which stands for Land Use Conflict Identification Strategy. So in this analysis done by Carr and Zwick, they looked at all different types of land use in Central Florida. I'm going to follow their methodology specifically for residential land use. So I'm just using kind of a subset of their analysis for this suitability analysis. So I have two primary research objectives. The first one is to identify the physical suitability of the land for residential development, and then the second objective is to identify the economic suitability for residential development. So for physical suitability, I looked at flood hazards and noise pollution. Now, to follow Carr and Zwick's model, I would have also looked at air quality, hazardous materials, and soil types. However, those were excluded from my analysis. I did download data for each of those, but for one reason or another, they weren't used. For instance, air quality, the air quality data that I had was a national data set, and so the spatial resolution just didn't quite work out. There was only one data point within the subject area that I was looking at. Hazardous materials was a very robust data set, but it didn't, it had a lot of data within it, but it didn't delineate that data very well. So there was no way to differentiate different types of uses. So like laundromats or gas stations were indistinguishable from heavier uses like industrial manufacturing. So because of this, I didn't want to use it. I thought it would skew the data a little bit too much. And then something that I'm really bummed that I didn't get to do was soil types. So I downloaded a soil types data layer from the USDA's website. However, it was in an older file format and a different format. It was having some issues with ArcGIS Pro, and I just couldn't get the data to display properly, and I couldn't get the data to work the way that I needed to. So rather than just bang my head against the table for hours, I decided to move on and just not use soil types, but I really do wish that I could have gotten that figured out. For economic suitability, I looked at existing residential land use, schools, hospitals, roads, airports, parks, and cultural amenities. So proximity to these things were all things that were evaluated as part of that economic suitability. So these, here's just a quick look at the data layers that I used and the sources from where I got it. So for flood hazards, I was able to get some data from the FEMA website. And for roads, USGS actually has roads for each state. and so I downloaded their road network map. And then for all the other data, I was actually able to use the city of Kansas City's data itself. So they have a parcel viewer where you can download GIS data. That includes parcel data, but also they have a layer called points of interest, which contains things like schools, hospitals, cultural amenities, and others. I was able to pull those out of that points of interest data layer. Also, here's just a quick look at the flow chart. First I define the subject area, then I clip the data that I have to the subject area. I recalculate the land use code. I'll go, well, I guess I'll just talk about that now. So there was like 50 or almost 60 land use codes for the city of Kansas City. So I had to reduce those down and join those. And there are multiple different types of land use for residential. I had to combine those into a single use, and same with commercial, and all those different things. I whittled those down to 16 different land uses that I was then able to use for this analysis. And then after that, I separated those things. So I separated the schools, hospitals, cultural amenities from points of interest. I separated local roads and highways because those are going to matter. And then I also separated parcels by land use. I'll go more over that in a second. So the first thing that I did was select the subject area for the project. So I took the area plan boundaries, the three areas that you saw on the beginning of the map, the KCIA, Gashland, and Stroll Creek Valley subject areas, and I selected those. And then I created the feature class called subject area distinct, which had the three distinct areas. Then I dissolved that and had the subject area dissolved, which is just a single polygon for the whole subject area. And then I used a buffer to create a 2-mile buffer around the area. Now the buffer is a really important component of this, and I can talk about this more on a different slide, but the buffer was used to prevent edge case scenarios. So that things that were nearby but maybe not in the subject area were included in the analysis. So that's really important, and I'll go over that in a second as well. So after that, I clipped the feature classes to the subject area buffer. I used an iterating tool in Model Builder to iterate through that, and I clipped that. And then just because the way I had it laid out, it did clip the area plan boundaries, but I deleted that because I didn't need that. And then I selected these subsets of data from the input data. So points of interest, I pulled out schools, which included universities as well as K-12 schools. I pulled out hospitals, and I pulled out cultural amenities. And then from the roads, I separated highways and local roads. This was done because being close to highways was seen as negative. Being close to local roads was seen as positive, so I needed to split those up. And then for parcels, I pulled out a bunch of data layers I didn't end up using, but it was interesting to see nonetheless. But for this specific use, I pulled out residential land use. I pulled the airport from the parcel level. I pulled cultural amenities. I used the points cultural amenities, but I pulled that anyway to see what it looks like with the parcel level. And then I used parcels not suitable for development, which was basically the existing development. And then I used parcels suitable for development, which were parcels that were undeveloped or agriculture or things like that could potentially be used for development in the future. So that's going to become important later on. So these are the feature classes, the cleaned feature classes that I used. I put SAB in front of them. It stands for Subject Area Buffer, and that helped me understand which ones I was actually going to be using for the analysis. So for each of these input for each of these feature classes that I had just created. I ran this tool, the distance accumulation tool, which creates a raster image kind of showing the distance from the input data within the subject area. So this replaces the Euclidean distance tool. Carr and Zwick use the Euclidean distance. However, ArcGIS Pro has no longer supports Euclidean distance, and it is it's still available in ArcPro, but they recommend you use distance accumulation. So that's what I did, and I did that for each of the feature classes, and then I got this as a result. So this is the results of the distance accumulation raster calculations. And there's some interesting things here for sure. So first of all, look at airports. There's the big, on the west side, the big green areas, the Kansas City International Airport. And nearby, and there's a smaller airport. From what I could tell, I thought this was a mistake maybe, or maybe it used to be an airport, but I left it because the official city of Kansas City's parcel land use codes identify it as an airport. So I did leave it because that's what the city data had, although I think it may be a mistake. The cultural amenities, you can see those points, access to schools and education, highways. Hospitals is a really interesting scenario because there was only one hospital within the buffer area. It's actually not within the subject area. You can kind of see that. So had the buffer area not been in place, there would be no hospitals included in the analysis. But because there is one nearby, you can actually include the distance to hospitals as part of this calculation. Now, I do wonder if I maybe should have used a larger buffer, because on the east side, where it's kind of white, the furthest distance from the hospital, within maybe even a quarter mile of the buffer boundary, there's actually another hospital. So those areas are actually quite close to a hospital, but it's not reflected in the map, as well as there's another hospital in the northern part of this area. So the hospitals illustrate the importance of the buffer area, but also that maybe the buffer area could have been a little bit larger. Then you can see local roads. There's lots of local roads. Again, I think that, I only noticed this when I was putting together the PowerPoint here, but they include the airport runway as in the local roads thing, the USGS data, and so that's that probably skewed the data a little bit, but had I caught that earlier, I probably would have removed the airport runways. And then you can see parks and existing residential development, and there's lots of that. Of course, this is within the city limits of Kansas City, so there's going to be a lot of residential development. There's not as much agricultural land use, but there is some, and quite a bit, to be honest, in this. This is less developed than the urban core, of course. So this slide shows the actual reclassification and raster calculation tools that I used, and kind of the final step of the process to produce the end result raster images. So for those the raster calculations from the previous slide were used and reclassified on a scale from 1 to 9. So for positively correlated things like hospitals and schools and existing residential development, things that were near were given a 9, a most suitable, and things that were far were given a value of 1, which is least suitable. And the way that these were calculated was using zonal statistics, and I calculated that by using the method that Carr and Zwick have in their book. So anything that has the median value the mean value or less was just assigned a 9, and then for each quarter standard deviation you go down one number, and until you get to 1, which that's kind of a leftover. Anything beyond that, higher is given a value of 1. So and then for the things that were negatively correlated, like the proximity to the airport and proximity to highways, were kind of the inverse. Although I didn't use the statistics for that, I just used the values that were in Carnswick's work. I thought it would just make sense to use what they'd already done, or they've already kind of prescribed for that. So once each of the distance accumulation rasters were reclassified, I used a tool called Raster Calculator to combine those rasters into for different categories. So first, I looked at the physical suitability from objective 1, and I combined highways and the airports to produce a noise pollution suitability raster, and then I combined that with the flood hazards raster to get a final result for objective 1, the physical suitability. So that's what this this is the output of that raster calculation. You can see the kind of veiny looking things are the flood hazard areas, and you see the highways. I do think this, if you're paying attention, you might start to see why there's some problems with my end result here. A lot of this is very suitable, like with the pollution, noise pollution, even though it's near the airport or near highways, they still are very very suitable, and I think that's maybe a misrepresentation of what, but this was kind of the model that Carnswick used, and I followed that pretty closely. So then for the economic suitability, I did the same thing. I combined multiple rasters together, but I did so using a weighted average. And so for this, you can see the various weights here on the screen. And that you can see that it very much favors existing development and proximity to local roads. And I actually think that there's some issues with this. I used Carnswick's weights for this, and they admit in their analysis that they just kind of followed their intuition. They did what felt right, and so it's not very objective, these values. And then I do think that existing residential development and local roads is somewhat counting the same data twice. So local roads are generally go to where people live. Like most roads are roads to residential development. And so I think you're inadvertently capturing the same data twice, and you're weighting those both the heaviest. So you're really putting your foot on the scale for existing residential development, and I think that kind of has some negative impacts on the final result. Speaking of which, so this is the kind of final result. I took both of those previous images and I used the raster calculator to combine them. I didn't weight the average, I just used the average of those two. And then I clipped that to the initial subject area, and then I overlaid the existing development over top, so that you can see the suitability for areas that have not been developed or that are available to be developed in the future. So as you can see in this image, it very much skews towards suitability. I'll go more over that in the next slide, but there's lots of green, lots of areas that are very suitable for residential development. That was a little surprising, a little bit more than I expected, to be honest. So that's where these statistics come in. So I actually ran the zonal statistics to table tool 3 times with 3 different sort of scenarios to get a result. So the first one I ran without taking away the existing development. So for that one, these are the full areas with the existing development not really being considered in the calculations. And you can see that if you look at the median and the mean, these skew very high. So for like Gashland, the mean value is 8.2. That means that the residential suitability for at least half is like very, very suitable. That seems somewhat unrealistic, to be honest. And you can kind of see that in the minimum value calculations here. They are 3.8 and 4.2, meaning that there aren't any pixels in these areas that are not suitable for residential development, which I think raises some questions on the validity of the analysis. So then I did another version of this where I set values of that overlapped with existing development to a value of 1, not suitable. And you can see that the same number of pixels, same square area, or same square miles, but you have minimum values of 1. And now you can see the median value is 1, meaning that most pixels in the raster are not suitable and are part of the existing development. So this obviously reduced the mean by quite a bit, and I think that this also is not necessarily suitable because the existing development is really skewing the data. And then lastly, I did one where I just clipped out the existing development and looked at only the areas that could be developed for future, the areas that are kind of green fields that are available for future development. You can see the pixel count is much less and the square area is much less. Now the minimum value is still 1. It should actually reflect the minimum value of the first group, but I did this after setting the existing development, the existing values from the existing development to 1. So there may be a few pixels here or there that are stragglers, and that's why the minimum value is 1 here. But take that with a grain of salt. You can see here that the median and mean values are still very high. The mean values are in the 7 range, which is still higher than you would expect. You know, you would expect that the mean values would be around 4, 5, or 6, but they're very high. And I'll go over why I think that is here in a second. So one of the things I did following this analysis and looking at the results, I compared my analysis with the City of Kansas City's future land use plans for their sub-area plans. Now, it's difficult to do a one-on-one analysis or one-on-one comparison because their future land use plans don't look at suitability, but they rather look at just prescribed future land use. So I did look at the areas, and the areas that had the highest suitability tend to be areas that are designated residential here, and areas with lower suitability tend to be non-residential land uses. So it's likely that someone at the City of Kansas City did a similar analysis when developing these plans. Now, I do want to talk about 2 areas that I think are major issues with this analysis and cause it to be somewhat inaccurate or not a good representation of the real world. Number 1 is the lack of topography used in the analysis. So I'm just kind of guessing here, but Carr and Zwick, they didn't use topography, but they were in Central Florida. So I'm guessing that they didn't use topography because it wasn't really relevant to what they were studying. The topography in Florida is relatively flat, and they were able to get all the information they needed regarding topography using flood data. And so in this case, I think topography, particularly looking at slope, would be incredibly important for calculating suitability. Um, if you have a very steep area, that's obviously going to impact the ability for it to be developed. So that should be considered um, for future studies in areas such as Kansas City or really anywhere that is not completely flat. And then the other thing is the raster calculation value inflation. So I believe that the values were so skewed to the higher values because of the way that the raster calculation, you take the average value of the pixels, and that artificially sort of inflates the suitability each time you take those averages. And so I think that's what's causing the problem here. So like for instance, if in the physical suitability raster you have a value of 1, and in the economic suitability raster you have a value of 9, and you average those together, the output pixel will be a value of 5. And so that, let's say that the value of 1 was because it's in a flood hazard zone, but it is nearby to a existing development, and it is nearby to roads, so it's very valuable from the economic suitability. But does that mean that it's valuable, that it's suitable for residential development because it's in a flood zone? I mean, the flood zone should take priority, right? So I think an alternative method needs to be developed, and I think the best way to do that would be to take, when you combine two raster images, rather than average the two results together, you would just take the lowest value of the input raster. So in that case, if there's an area that's really suitable economically, but physically it's not suitable, it should still receive a 1 value or a low value to reflect that lack of suitability. So I think that's something that really needs to be considered um, for future studies. I'm hoping to use this method to do my thesis. So I've learned a lot of things that I need to improve upon and things that I could do better, and I'm certainly going to be considering that and how I can improve that for my thesis. I mean, that completes the presentation. Um, I appreciate anyone that watched this video. Best of luck. It's been great doing classes with y'all. Thank you.